Welcome to Impact Quantum, where we unpack the future of computing. Today, we explore trapped ion quantum tech with Mahmood Sabooni from Open Quantum Design.
From lasers and vacuum chambers to open-source quantum hardware, we dive into how trapped ions might shape the next generation of quantum computing.
Well, hello and welcome back to Impact Quantum, the podcast for the quantum curious. We firmly believe you don't need to be a PhD, although it certainly helps, to participate in this emerging field. And with me is the most quantum curious person I know, Candace Gouhely. How's it going, Candace?
It's great. Thank you so much, Frank. You know, today it's crazy this week, actually. We got a massive snowstorm. And although where I am in Montreal, Quebec, like we always see the first flakes for Halloween, we normally don't have such a deluge. Like I probably have 9 inches outside. It's just crazy. So I'm all looking at the beautiful snow, but I'm getting my head all in gear to have a great conversation today. I'm really excited about our guest.
Yeah, awesome. It is chilly down here. We didn't get any snow, although I think in Western Maryland they did get some snow. But it is chilly here, and I may have to fire up the GGX to do some fine tuning to heat up my office, as well as turn on some of these monitors. So who do we have talking to us today, Candace?
Right. So today we're talking to Mahmood Sabooni. He is the lead quantum processor engineer at OQD.
Very cool.
Hi,
and
how
OQD?
are you today?
Okay,
At
yeah,
OQD,
that's thanks for having me here. Yeah, here also we have a little bit of snow, like last couple of days. Still like leaves on the trees, but you could see snow, and then after that you see the leaves on top of the snow. That's kind of interesting feature that you could see.
So you're also in Canada, right?
Yeah, in Waterloo, Canada. Yeah.
Okay, very cool.
For the people who don't know, like Waterloo, where is it? Like close to the Toronto, like 70 or 80 kilometers south. Yes, that's I'm here from probably almost like 10 years. Started by like some postdoc and some other activity at Google as a optical engineer, and then back to this open quantum design startup in Waterloo.
Oh, very cool. Very cool. Your LinkedIn is very impressive. So I have plenty of questions around that.
Sure.
Open quantum design. Tell me about that. That's an interesting. What does open quantum design do, or OQD?
Yes, that's probably the core of the discussion that we can go through. First of all, I'm more like a hardware person. Like I worked more on the hardware side on like quantum information since my PhD, which was in Sweden in Europe, and also my master there. Around the quantum information technology and like storage, basically quantum memory during my PhD. And after that, I came to the like quantum computing parts, and as a postdoc here at IQC, and I just put some gap for the Google time, which was more classical optics and hardware. But later, like there is some 3 PI here in Waterloo, 2 of them, Crystal Senko and Rajul Islam, working on the ion trap machine, and one, Roger Molko, working more on more AI and software side. They decided to start making like an ion trap based full stack quantum computer. This company started from like February 24. And I joined them at the same time. Then the idea is to have a full stack quantum computer based on ion trap available for anyone who wants to rebuild it. Like the way that we do is that we have like some software team and some hardware team. I'm more on the hardware side, and we are developing like some prototype. And at the same time, we put all our designs on GitHub, available for like anyone who wants to rebuild or use that kind of module for his setup in future. And the big picture is to like do the same thing that happens for either software or some even hardware in the classical computers, in the quantum computers. Like there are some, like I can explain more detailed, like what kind of reasonings is behind this. Will be successful or not, that we don't know. But we're pushing that. And during last year, we could reach to some good milestones. We could get some collaborators, like a partners. We have like 5 different companies already putting money or full-time employee on this open source activity. And we are pushing towards like getting our first like a spec of the machine out soon. Hope like a January 26th that shows, okay, this machine is already live and available. And yeah, looking for like more people to come and contribute to see how we can push it forwards. That's the more like a central activity of the open quantum design.
So in practice, what does open quantum hardware design mean in practice, and how is it different from traditional closed or proprietary approaches in physics research?
Yes, like if we want to make very similar example in the classical world, I could bring the example of the RISC-V company. That's a company that actually we have some people from there also, like with the same idea, came to the One Quantum Design as a board member to push the idea here also. In 80s and 90s, there was like a discussion about the designing of the CPUs, like different companies, like closed or open, that start to like work on that kind of architectures, and then at some point, RISC-V as an open source company start like building the standards for designing chips. And these days, like that, the RISC-V, it has already 70 plus members. And then most of the CPU design in Intel, AMD, anywhere else, it's using those standards that's built on the open source activities. The same idea here also could be in principle implemented. Like for example, benchmarking of the quantum computer is something which is very tricky. Like different company, like plus 10 different companies already announcing different machine, and then we don't have still fully standard benchmark system to do the benchmarking on different machine. And one of the reason is that those machines are closed, and that no one have access to those machines to test and benchmark them. And then if we have some machine, at least in some of the architectures like Iron Trap, or in future could be others also, you can run your algorithm on that machine and test that machine, and then test your standards, and then write the standards based on those open access machine for anyone around the world. And then the rest of the people can also use that. This is not against any IP-based company also, like they could also get benefit of this open source and build the standard around that, because around this like a point, people can come and exchange idea and also develop whatever that they have done so far, and then integration of those like a multi idea people can in principle maybe outperform the closed system. Yeah, that's the idea behind this. But there's some other feature also would be interesting from hardware point of view, because from software point of view, you can see a lot of comparison around the board. For example, Linux versus Windows. Like maybe the top, like a most important project around the world, running Linux, not Windows. Like a Linux is the open source. That's right. In the software, it's very clear that that's a path that can be very successful. In the hardware regime, especially in quantum computation, very expensive hardware you need to develop, and then the open source community will have difficulty to gather those together and then test whatever they want to do on that hardware. The idea on OQD is to make that kind of test beds for anyone who want to work to single details of the machine, like other machine that is available already, mainly is cloud-based. You can run some algorithm on those, but you don't have access to full ingredient of that machine. That's simply because of the IP reason. But here, everything is transparent. You can see each single module, and for that reason, it will be easier to first benchmark it. Second, also learn it. From this hardware available, a lot of people like a software oriented that they are interested to run some calibration on some real quantum machine, they can do that, and that's a big benefit on the learning curve. Build some better workforce development, or even for closed system, they can use this kind of people who know it's capable of doing something which was not possible without access to the hardware. That's one big plus. And also, for example, colleges that they want to train some quantum engineer at the bachelor level, that they want to handle quantum machine, they can use this kind of system. They cannot go and buy some quantum computer from big IP-based company and then have access to all full details because it's IP-based. But here they can have a machine and then run it and learn it and improve it for whatever purpose that they have. This machine is not necessary to be the top best machine in the world. It's just need to run some simple functionality. And because of the reason that I mentioned, like benchmarking, you can do it on a simple machine. Learning, you can do it on the simple machine, and also workforce development, also you can do on this machine.
So with the open design, transparency, open source, do you find that this accelerates innovation, that sharing these designs actually helps solve complex engineering problems perhaps faster?
Yeah, that's the idea. If you want to compare it I'm a physics person, and then I was comparing to some phenomena in nature, comparing the light bulb to the laser. The laser happen whenever that you have phase coherences of the photons on top of each other, and they will amplify the final result. Here also, that could be it's difficult to prove it, but there was some example, as I mentioned, software development and also hardware, like this RISC-V versus ARM or Intel, that shows that was successful. Here also, there's a good chance that can be successful. And this comes from University of Waterloo. Anyway, they spend time on development different sections and different modules. And that would be good to share it with the academia first, for sure. And then why not share it with everyone? And then try to also, we also could benefit a lot. For example, we have some locking mechanism on our laser that we don't have much and bandwidth of the people to develop that, but someone else could come and say, oh, I did this. And with all single details, not just the paper, not the published paper or archive version, just with the details of the electronics, mechanics, optics, diagrams, and share those information, and then we can build that system in here. On the other hand, the other partner also can benefit from our whatever, for example, our optical circuit board design, which is transparent, everything available, and use that as resources to build his own system in different country completely. Yeah, we have some collaborators from India, from Brazil, from a lot of countries in the South hemisphere, coming for this kind of options. And of course, there will be also some difficulty in terms of politics that will be challenging to how, when, and where you want to distinguish between these open and closed and IP based. That's a still open question. That yeah, there is some resistance sometimes.
So there's a lot to unpack there, but one of the things I saw on your website for OQD was you referenced the term full stack quantum computer.
Yes.
What is a full stack quantum computer?
Full stack means like you can the whole quantum computer is several layer of different information from your classical computer code, and then that will convert to some mid layer, and then the mid layer to very low level in the, we call it like a meta layer that you want to talk to the, in our case, to atoms. And there will be a lot of like exchange in between. At Open Quantum Design, we have some partner that works on the software. Like for example, Xanadu as a IP-based company, they provide some agreement to OQD and provide some full-time employee. They can adopt their like a software which is open source to our hardware, which also is open source. Like we are working on OQD Eintrab using the Arctic software, which is the open source hardware developed by I think it's from Maryland actually. And these two combination could be as a full stack. Like you can run your code high level, and then it will convert everything down to the pulse level, talking to atoms, take the data, and then plot the data, extract the information, and use it. That's the meaning of the full stack, like from high level to bare metal layer, and vice versa. Open to everyone. Like the software, it's in most cases are available that like in superconducting qubit, in photonics. And Eintrab, it's a little bit lagging. Like we need some software at the high level. That's this kind of project trying to fill out that gap. And yeah, that's the meaning of the full stack.
Interesting. Full stack is one of those terms you hear a lot in technology, and it means different things to different people, and it means different things in different contexts too. So that's why when I saw that, usually my reaction to the term full stack is it triggers me to flashbacks of conversations I had with recruiters throughout the years. So I'm like, no. so I like your definition better. So
okay, yeah, here is like a more like a simpler version that yes,
much more reasonable version too.
yeah, of course, for like using the quantum computer, you cannot directly go to the bare metal. You need some middle layer, which is very crucial, and still needs a lot of development connecting those hardware in terms of, because one of the enemies here that we have in like whatever properties that it will make a lot of difficulty for us is the phase. Phase means like whenever that you have a wave, you need to predict exactly in future in time what is your amplitude, and this could jitter a little bit. And in our hardware side, this will be crucial to control this phase. And in the radio frequency hardware, it's a challenging. That's not in our expertise, like a bandwidth in open quantum design, and we are trying to get help from like some expert in the RF. There is nothing available, I could say, reliable for especially for Eintrab, that you can use it easily and control your ions or your atoms. And even in the closed system also, which is very expensive. It's not fully functional to control the ions yet. And yeah, we have some gap there that we need to fill out, controlling the phase reliably in the open source community, which is, as I said, is based on the Arctic and Sayonara Box. It's a company for ion trap. The same like a company like other names coming to the superconducting qubits also. They're a little bit ahead than ion traps if you want to compare it in that area.
Okay. Ion traps. You don't really hear. I haven't heard a lot about that lately. What exactly is an ion trap versus
superconducting?
For superconducting, like what? How does that relate? I know it's one of the hardware kind of families.
Yes, but like for any quantum computation, you need some species, some people using photon, which is like a photonic-based quantum computing, like a Xanadu or PsiQuantum. They are using photons. Some people using a atom directly, single atoms. That's like a neutral atoms, like a Q era, for example, using this kind of species to encode the information. And another type of quantum computer that using species of ion means like you have atoms and then you shoot out one of the electrons ionized. Why you make it ionized? Because it will be easier and deeper to trap it. What the trap means, like you need to have like atoms, and these atoms, single atoms, no interaction with the environment, and then levitate in whatever area that you have. We have a vacuum system. We push atoms inside, like evaporate atoms to the vacuum system, and then shoot the laser to the atom, a bunch of atoms, 10 to 20, 10 to power of 20, like, and then ionize atoms, send electron out, will be ion. And the ion, because it has a charge, you can trap it with a DC and RF voltage. And that trap is very deep compared to the neutral atoms. Neutral atoms is shallower. Like if you some other hydrogen atom inside your vacuum system come and hit the like atom, can kick it out. But in ion trap, it's deeper. Like you need more energy to kick it out. Then if you trap like one ion in your vacuum system, you can have it quite long, for a day or two, and then do the experiment with it. Compared to the neutral atom, which is like quickly will escape and you need to trap it again and again. But in terms of the physics, they are quite similar. Like the way that we trap is different, but in terms of physics, you can find a lot of similarity. Yeah. Compared to the superconducting qubits are circuits, like in principle are electronic circuits in the quantum level. Like they have some nonlinear component, like in the normal electric circuit, we have R, C, L, but they have some component which is nonlinear, and they can work as the source of making the energy differences and make a qubit. They are handmade compared to the atoms, which is natural. Like it's very difficult to make 10 quantum bit in superconducting qubits similar exactly because it's handmade. But in atomic world, they are similar in nature. In that sense, it's easier to start with, but the difficulty will come afterwards when the engineering comes. Like the electronics supports a lot the superconducting qubits back in 80s, 90s. Then there's a huge engineer development there, which is missing in atoms and ion community. If we could fill that gap, they could outperform the superconducting qubit because naturally their properties are better. That's the differences between these two, like a way of or three photons, superconducting qubits, and atom or ion base.
Okay. So there's a lot of precision that goes behind the ion traps. It's very exciting. You get lasers, vacuum chambers, electromagnetic fields, all these mind-blowing ideas all working in harmony. What's the most challenging part of building or maintaining an ion trap system?
At the moment, the scalability. That's the challenging part, and the rest is manageable. Like you can have recently Quantinium published like a 98 qubit, and with the like benchmarking, when I say there is some spec of your machine that will define how it's working. In terms of the element level and in terms of system level. And there's a huge people that like working on this benchmarking different like a machine. And what was the question? I forgot.
Oh, saying what was the most difficult?
The difficult, like scalability. Then you want to increase this like a 98 qubit to 500 or 1,000 or 10,000 or 30,000. How you want to do that? That's challenging. Like different architectures already like is under investigation to see how we can do that. Yeah, two main way to do for the ion trap is either do it like a node base, like have 100 qubit here, 100 qubit somewhere else, like within like acceptable range, and then connect them with photons. And then that way you can extend and scale. That's one approach. That IonQ and Oxford Ionics recently starting that kind of approach. And also another approach is it's called QCCD. Like you have like core center, and then you transfer physically your ion to somewhere else and do something and bring it back. Like transferring between different nodes that you have. That's also another approach that some company is using that approach to reach to scalability, but still is very difficult challenge to overcome. And like a company put like a 2030 or 2035 to reach to some level of 30K level of scalability. Like a number of the qubit that you have plus the rate of error that you have each single qubit.
So do you think the trapped ion systems will eventually power commercial quantum computers, or are they more likely to remain like the gold standard for scientific precision and benchmarking?
Yeah, it's a difficult question, but the paper publication that you could already see in terms of system benchmarking, like system benchmarking means that you have some specific algorithm and you give it to me. I will run it on ion trap machine. You give it to the second ion trap machine. You give it to the neutral atoms machine. You give it to the photonics machine, superconducting machine, and compare the result in terms of accuracy and the time that it takes to get back the data. Like an ion trap, it's top now, like with the error rate and even with the lower number of the qubit compared to, for example, superconductings. But in terms of the overall, like a benchmarking, is still it's better than superconducting. But this question, it's a very difficult to answer. There's like some other competitor, like a photonic base. They're claiming for 1 million qubit, but it's not out there yet.
Right.
But it could come. Like, who knows?
Yeah. So are sheer number of qubits going to matter, or is it logical qubits and there's physical qubits? Like, is there? I think what I really want to know is like what trapped ions. Annealing is good for one type of problem. Photonics are good for where does trapped ion really like shine?
Like the original question that you mentioned was about the logical and physical qubit.
Well,
right?
yeah, I know. I had way too much coffee, so I dumped a couple of questions on you. Sorry about that. But the first question I want to ask, let's hit the undo button on that. Trapped ions. What problems are they like really perfect for? is really the question I want to know. Like where, if I'm looking at a whole suite of problems, annealing is good for one type of thing, photonics, where does trapped ion really excel? Because
Yeah, I think the target for trap ion is the universal quantum computation. It's not just annular.
gotcha. Okay.
It's like, any algorithm that you can give it and get the answer. It's a matter of like a quantum volume, like a number of a qubit, error rate, those kind of things. But the target is to solve like a hard problem that the classical computer cannot. That's the target.
Gotcha. Yeah, because I can easily see like, kind of I'm old enough to remember the early like Wintel days where like this is 100 megahertz, this is 150 megahertz, this is 166 megahertz, right?
Yeah.
Like that became like a marketing scheme. Like, and I know that there was a speed boost attached to that, but
yeah,
beyond a certain point, it was not really a meaningful measure of how fast the machine is. And it seems to me that quantum, like number of qubits and that's even more complicated. And number of qubits does not necessarily mean number of logical qubits. So it seems like at some point when this becomes real, and not that it's not real today, but when it becomes something that, you'll see ads for, how are they going to be measured? Like, how do you compare one quantum computer to another? Like,
that was the question actually. Candace mentioned that benchmarking has several different like layer.
Right.
You can benchmark different like component level and say, okay, I do 1 gate, 2 gate, and the spam detection with this much error. That's very good, but it's not the whole story. The whole story is that you give me a sample algorithm, that it's a standard algorithm, and then you can run it on classical machine and see, okay, it takes 10 to 25 years to be solved, and then run it on like a quantum computer and then see how long it takes and how accurate the result is, and then compare it with the other machine. Like this type of benchmarking is ongoing. Like a lot of quantum machine that is out there, they are publishing based on that kind of like they're trying to publish several algorithms, 1, 2, 3, and the paper, and saying, okay, we did this on this machine, and then this is the result. And then even they compare it with some other machine back to back, then show the result, how like how much error, with how much uncertainty you can give this answer. Those kind of measure. It's a more system level benchmarking. That's more important at the end of the story.
I gotcha. All right, that makes sense.
So for students or engineers who are fascinated by trapped ions, what skills or areas of study would you recommend they start exploring now?
Yeah, definitely start with physics background and AMO physics, atomic and molecular physics. That's a core for understanding the single ingredient inside. But at the moment, we need a lot of other skills need to be developed also, like optical engineer. Like we need to take the data from atoms or ions to our detector, and then we need some collection system and imaging system, for example. That's very important. Understanding laser, how we can use the laser, how like we can control the different spec of the light. That's very important. And either mechanical engineer that comes with the game, because you need to make like here at OQD, every term we hire several co-op students that we have in here in Canada, that the students in the bachelor level in mechanical engineer should come to some company and learn for something for like a 4 months, and they have to be paid also. They come to this machine, and then they helps us to build some optomechanical modules that we need to make it with specific spec to build our whole machine. That's also important. It's not to the core of the like ion trap, but it's very super critical. To show the criticality of this like making mechanical stable system. Like we have 30 ions sitting 4 micrometer beside each other, like 120 micron. And then this is the like a line of the ions that we start working and doing quantum computation with them. Like the thickness of the hair, human hair, is 100 micron. Like this, like a string is sitting at the cut of the human hair. And then you need to control each individual atoms with lasers. And then the laser that you're talking with atom number 1 shouldn't talk to with atom number 2. You shouldn't have crosstalk, like 4 micrometer away. And 4 micrometer away. And then you can imagine how stable your mechanical system needs to be to not make these two mixing each other. And it becomes very important indirectly to the main problem. But for people who are interested, as a builder or as a user, 2 different categories. Like builders are the people who should know about the atomic physics, this laser, optical engineering, mechanical, electrical. Users, they should know more about the software. Because
Right.
like whenever that you use your classical computer, you don't ask about like how the CPU is built. Like,
Right.
but you use like the software level, like more theoretical physics will be the user. Like the comparison will be builder of telescope and user of the telescope. Like there's like a 2 different category, and we are in the builder side at Open Quantum Design. We are building the machine, and then some people coming from theoretical physics can come and use it afterwards.
That makes sense. That makes sense.
What's the most surprising or beautiful thing you've ever seen happen when working in a quantum experiment?
Yeah, like you see some unexpected effect, and you see that's kind of noise, and then after some investigation you see that, oh, that's another phenomena that it's kind of coming to your game and showing, and it, then go to the theory and see, oh, that's kind of interesting things to develop. Even sometimes you will be sidetracked to that kind of problem and see some achievement happen at that kind of noise that you saw in the system. I've seen several of these examples on my own research. It's kind of very super interesting and exciting.
Yeah, I also wonder too, like, how much of it is you get this like, is my equipment like messed up, or is my seeing a new undocumented phenomena, right? Like,
Yeah.
there's probably a bit of excitement and a little bit of skepticism and a little bit of like, not sure which it is.
Yeah, that's very important in the aim of physics lab. One of the differences that I should highlight here is that have you ever been in like a experimental lab, like AMO lab?
I have
Like,
not, no.
No, it's kind of very super messy, everything, like the cables coming, lasers and the mechanics, and then in principle that system works just once, and then paper published, and then second time you don't know that it's working or not. You need to spend a little time to, like, in principle, students spend like a 90% of the time to fix the problems ongoing, and then probably 10% doing real experiment.
Right.
On a normal like AMO labs. One of the goal of the OQD is that change this ratio to lower value, like try to make the system more stable and more modular in the way that we can monitor different sections and also make it stable overall, working for a long time. More work as like a commercial product compared to the like a R&D product. Like a comparison will be like a breadboard in electronics, and then the PCB version. Like breadboard is the time that you do testing, and then PCB is like a solid. And in OQD we try to go from like a breadboard version, messy version, to more solid and PCB type version, and try to change this balance. Like spend less time on fixing problems, spend more time on doing the experiment actually. That's one of the main goal here. And we could see, like, we have another lab beside the OQD that is R&D based in the grandpa of our lab. And we could see, like, the thing that they spent like a year to achieve, we could do it in like 2 weeks. That's very, very distinct value that you could see. We have a lot of camera photodiode in our system, probably plus 100, that monitor different level of the system and report the errors. And that will help you to maintain the system commercially, not as a physicist, as a more engineer.
Okay, interesting.
So there's a lot of kind of interdisciplinary collaboration that's happening
Exactly.
in quantum development, right? You've got your physicists, you've got your engineers, you've got computer scientists. So how do you find the shared language so that you're able to kind of bridge those disciplines effectively?
Yeah, someone who has like a little bit of each one of those should be on top of the project, like should lead the everything. Like a person who knows a little bit software, mechanical, optics should be on top of that too. Whenever that you hire someone from a specific vision, can get benefit of his like experts knowledge out. Yeah, that's very crucial to have someone who has done a little bit on some of those kind of activities.
Okay.
Yeah, for people who probably interested, you can later put like Open Quantum Design link and also GitHub to the people who are interested to see what kind of things already it's on public level that everyone can see on hardware and software. We have also some simulation level, which is very important also from aim of physics simulation, that anyone who want to run anything can use that from our GitHub. And this GitHub will be more and more published in future whenever that we get like some spec of our prototype, and then they could have more information of each individual module that we have here.
Okay. Interesting. Yeah, I think there's a lot to say. Like, it seems like quantum computing is going to need a lot of multidisciplinary and people. So I think, would that be good advice for people? Like, if you're really good at one thing, learn a little bit of something else.
Yeah. And actually, I think from the report in the North America, I've seen some like a publication that there is shortage on the workforce for quantum development. That's interesting, and that's coming from different kind of principles, as I mentioned. It could be completely not relevant to the quantum world, but it's directly relevant to building the quantum computer.
Right.
So how close are we really to seeing quantum technologies like quantum memory or quantum internet change our everyday lives?
Yeah, I think we like a quantum related phenomena is already affect our life. Like whenever that you are using GPS, you're using atomic clock. That's definitely direct use of the quantum world in daily application. If it comes to the quantum memory, also my PhD was on the quantum memory phase. There are already some companies that building quantum memory and quantum repeaters across the world, testing across like 100 kilometer fiber, and that will be crucial also for future quantum like a cryptography or for quantum computing even. Like some company already doing that. And for quantum computing, it's a little bit further out. Like quantum memory, quantum communication, quantum sensor is closer, and you have some product already. But quantum computing, it's a little bit back, and still we're not there to say this is directly used on our daily life. But some problems like finding the proper drug, for example, that's one of the things that the quantum computer can affect. If you have a quantum computer, like easily can break your like a cryptography that you have for bank account these days. That's a threat to the like a daily life. That if it comes to the reality.
And that's what it has a lot of people on edge about this.
Yes, yeah. That also could be something that will affect. But it's a very tough question to say exactly what will be there. Who knows?
That's fair. That's fair. I ask this question in every single interview, and I always love the answers. How would you explain what you do on a daily basis to a non-technical person who's not in your field, like just completely non-technical? How can you explain it and break it down?
You mean what in terms of what?
In terms of what you're doing in quantum computing, in terms of what problems you're trying to solve.
Is this the cocktail question kind of
yes
thing?
Yes.
Like, like if you're at a cocktail party or whatever, and what do you do? Well,
how do you break it down? How do you unpack it a little bit?
For like explain, like I didn't fully get probably the question, but explaining the problem that I'm working with in general, like a quantum computation. Which one?
I would say in general.
Yeah.
You get the question, what do you do, right? And you have to assume they're a civilian, right? Like they're not.
Yeah. I could go like I could say like for example, if you go to the beach and get one of those tiny sand on the beach that has 10 to the power of 20 atoms inside. One of those tiny sands. And here we are working with one single atom.
Wow.
That's probably can bring you in the scale size how difficult it is to work with this guy. In terms of the scale of your system control, for example, if you consider Toronto to London, for example, you want to report the distance between these two cities by nanometer scale.
Right.
That's also like in terms of scaling factor for controlling your laser light, whatever that you do that you want to control these single atoms, you need to have that kind of control. And we have that kind of control that we can report the distance between New York, London with nanometer scale. Then you can go to your cocktail party and think about this kind of things.
Well, we have a lot of folks who are, currently they're physicists, they're really in academia, and they want to go over the bridge into industry, where you are now, and they don't necessarily know how to navigate that transition. Is there anything that you could talk about in relation to that, the transition you took?
Yeah, the industry is, as you know, it's completely different world compared to the academia. For going towards that direction, like improving the skill set of like a daily activity and close some small like task, that's a very crucial for industrial level activity compared to the academia. The academia is more like a long-term plan, working on something for very long term. But in industry, you need to deliver something on some specific dates, and that makes you like decide differently. Probably your system that you want to close it is not perfect, but it can do the job that you want to do for that specific task. That kind of in terms of the mind level, you need to change your mind from like very optimized for the best system that you want to make it to the system that it worked for that specific task. And whenever that task finished, then the second task can like improve that. Third task can improve that. And then you will reach to the final goal, but in different way in industry. Yeah, you have some commitment to deliver some result in a team, in a big team, like a 40, 50 people, 100 people. They want to accomplish some goal. And that's very important to do your task on some specific tool, like task at deadline.
Interesting. Any other further questions? I know we're getting close to the top of the hour, and
well, I've asked my favorite cocktail question.
I know.
And that is my favorite one. I love doing that.
But it does force somebody to kind of like explain, right? Like, and I think that's also going to be an important skill going forward for anyone in academia. Like, you can't assume that people even know, like you said, 10 to the 20th power of that. Mm-hmm. You can't assume that anyone would know what that even means, right? Like, but no, I mean, that's important, right? Because, like, at some point, if you do want to make that bridge, you're going to have to stand in front of an investor and in front of a customer. You kind of have to explain like what this is, right? And that's I think that's a challenge every technologist, regardless whether it's quantum physics, whether it's AI, whether it's has to come across, right? The person, the hippo, which I don't know if you've heard that acronym before. Yeah. Have I used that acronym in front of you, Candace?
Yes, I've heard it. It's one of your favorite ones.
It also, is one
NIMBY.
of my favorite ones.
NIMBY is your other one that you love, right?
Yes. So
NIMBY,
hippo,
not in my backyard. I've learned that one. Tell them the hippo. Have you heard of the hippo? The hippo acronym?
Yeah.
Highest paid person's opinion. Yeah. I first heard it at Microsoft, and somebody was like, well, doesn't really. Not going to name who that hippo was, but that was pretty interesting. It was like hippo, like, and my mind went immediately to hungry hippos, and then it was like, no, this means like highest paid person. But you mean the highest paid person in any given enterprise is probably not going to have a background in quantum physics, right?
Yeah.
I think that's a safe assumption. Could be wrong, but again, but so you have to, the people cutting the checks, or you have to convince them that you're a startup, the value of it, before they write that check. And I think that this is something that this is what separates kind of like the famous entrepreneurs in tech from the ones who are not, right? Like, Steve Jobs, was he the most proficient software engineer or computer builder? No. Probably not. No. That was probably Steve Wozniak. Yeah. But what he could do is sell a vision, sell the end result. And I think that's where the magic is, right?
Yeah, this is the same like in academia world. Like you have some prof which is very, very knowledgeable, but they're not good at teaching, and vice versa.
Yeah.
Like this is the same thing. Like in industry, like presenting idea and compared to the knowledge deep of that kind of area, the same thing we have in academia also. Like,
Very
well,
cool.
I think that's a good point to leave us off on. I think that we've asked some really good questions today.
Yep.
I've loved everything we've been talking about. We really haven't had someone who's been able to focus on trapped ion for us before. So that is very exciting for us.
Yeah, that really is. Because like, I know that's one of the oldest. Like, so like it's something that like can't be ignored, and we've kind of ignored it up till now. So
yeah, great. That that was a good opportunity to talk to you.
Awesome.
And also, I heard about the other podcast during the last couple of days. That was also interesting to
thank
hear.
You.
Yep.
Thank you.
Thanks for joining us on Impact Quantum. Today's deep dive into trapped ion hardware showed just how precise and powerful this technology can be. If you enjoyed this episode, subscribe and stay curious. More conversations at the cutting edge of quantum tech are on the way.